This is the last topic of Unit 4, magnetism. First, the origin of the magnetic field. What is the origin of the magnetic field? When the charged particle moves, the movement of the charged particle is responsible for magnetic field. And what are magnetic poles? So, as the atom consists of a nucleus. Inside the nucleus, we have neutron and protons, and surrounded by electrons. So these charged particles are moving, and because of the movement of these charged particles, this atom will behave like a magnet. And when atom is behaving like a magnet, we call that as domain. So this whole atom is having its own magnetic field, and what we call that as domain. Then for a magnetic materials, a material which is behaving like a magnet, these domains are there, and these domains are arranged in a regular pattern. So when domains are arranged in a regular pattern, the material will behave like a magnet, or known as a magnetic material. For a magnetic material, there are two regions where the magnetic field is much stronger than any other part. So region where the magnetic field is much stronger than any other part, that region is refers to pole. So we always have two regions where the magnetic field is much stronger compared to any other part, and we call that as a pole. So for magnet, there are two pole. One is known as the north pole, another one is south pole. And the space around the magnet where there is a magnetic force can be felt by other magnetic material. The region where the magnetic force can be felt by other magnetic material, that region is known as magnetic field. And we represent this magnetic field by pointing or showing a direction always from north to south. So these are the terms which you should know for magnetism. What is the magnetic flux density? Magnetic flux density, it is refers to the strength of a magnetic field at any point. So like how much strong or weak the magnetic field at a certain point, that's known as magnetic flux density, denoted by B, and it is a vector quantity because it will have a specific direction at any point. The unit, the SI unit is Tesla. So magnetic field is measured in Tesla. Higher value of a Tesla means stronger magnetic field. Smaller value of magnetic field means smaller value of in Tesla means weaker magnetic field. Then what is magnetic flux? Magnetic flux means how many magnetic field lines are passing through a unit area. Like we have a region, say you have magnetic poles. So we have north, south, north, south. So magnetic field is from north to south. This is a magnetic field pattern. So it is from direction out from north and into south. Now, What is magnetic flux? Magnetic flux means how many field lines are passing through a unit area. So example, if we have this surface and this surface is perpendicular to the magnetic field. So how many field lines will pass through a unit area? So strength of a magnetic field on a unit area, that is known as magnetic flux. So stronger magnetic field means higher magnetic flux, and larger area, this will also show greater magnetic flux. But it is always measured the perpendicular, like how many field lines passing perpendicular to the surface area. If it magnetic field is making certain angle, then we will resolve the magnetic field into a component and find the flux. Like for example, if you have, say this is a surface and the field lines are making certain angle. So if angle with x-axis is given, so this angle was given with x-axis. So the component which is with an angle, this will be b cos theta, and against the angle will be b sin theta. So in this case, if we need the flux, area is given. So how to get a flux, magnetic flux? It will be b. We always take a perpendicular component to the surface. So perpendicular to the surface is b cos theta in this example. So b cos theta into a. And if other angle is given, it depends on which angle is given in the question. Say angle with vertical axis is given. So this one is b, the one which is with an angle b cos theta, and against the angle will be b sin theta. So this will be b sin theta, or you can also say this will be b sin theta. So in this case, the perpendicular component is b sin theta. So when we calculate a flux, so flux will be equal to b sin theta into a. So it depends on what angle is given, angle with x-axis given or angle with y-axis. So number of the field lines passing through a unit area perpendicular to the surface is known as magnetic flux, and the unit of the magnetic flux is Weber, denoted by WB. You can say Weber or WB. So with respect to this, unit of magnetic flux density can be Weber per meter square. How? Because flux is equals to B dot A, or B is equals to flux divided by A. Flux is Weber and area is meter square, so Weber per meter square. So you can write Tesla or you can write Weber per meter square. Both are equivalent, no difference. Is it clear, the concept of the magnetic flux? Magnetic flux refers to how many field lines are passing through unit area which are perpendicular to the surface. Then what is magnetic flux linkage? So because normally, like we may have normally what we have the unit area, like, but it may have more turns. Instead of having only one turn, we have a coil with many turns. So how many field lines are passing through a unit area in n turns? So that is refers to magnetic flux linkage. So say this was a magnetic field, and instead of having a wire with a specific area, you have n turns, like loop is there. Rectangle, it can be a rectangular wire or a circular wire, but loop. Like this is one loop, then this is a second loop, third loop, and so on. So in this case, what we called magnetic flux linkage. What is a magnetic flux linkage? It means how many magnetic field lines passing through unit area in n turns. So that is known as magnetic flux linkage. Also denoted by phi, but in this case, magnetic flux or so magnetic flux is how many field lines are passing through a unit area. But magnetic flux linkage means how many field lines are passing through unit area for n turns, like where n is a number of turns, how many times a wire loop, like 10 times there's a loop or 20 times a loop, so that will be n. Is it clear? So when we are calculating for one, we call that as a flux, but when we calculate for n turns, we call that as flux linkage or magnetic flux linkage. Is it clear, this part? So as we know, current is having a magnetic effect. When the current passes through a wire, the current produces a magnetic field. So if you want to find the direction of the magnetic poles, we can use the right hand grip rule. So according to right hand grip rule, fingers will turn in the direction of the current and thumb will point towards the north. So as you can see, in this case, the fingers as a current, it's a loop. So current is passing. Say you have an electromagnet, a wire is turned around on a soft iron core. This is the direction of the current. So your thumb will point toward fingers as you catch the wire in the direction of the current, your fingers right hand rule. So if you grip the wire in the direction of current, your thumb will point toward north. So left hand side will be north and right hand side will be south. And the magnetic field will point from north to south. Around the wire, it will be circular. Within the wire, it will be straight. So using a right hand grip rule, we can identify the magnetic poles, and using a magnetic poles, we can sketch the magnetic field. Same way, if the wire is a straight wire, then again we will use a right hand grip rule. But in this case, for a right hand grip rule, the thumb will represent the direction because it's a straight wire. So opposite will happen. That thumb will represent the direction in which the conventional current flow, and fingers will turn in a direction of magnetic field. So if you grip, your thumb is pointing, like current is going up. So thumb is pointing up and the fingers turn, automatically shows the direction of a magnetic field. When you represent this magnetic field, you have to keep in mind like first two field lines should be closer to each other, but then the distance between them will increase. Why? Because when magnetic field lines are closer, it shows stronger magnetic field, like higher magnetic flux density or magnetic flux. But the distance increase, so magnetic flux or number of field lines passing through unit area decreases. So you can see the first two lines are closer, then the second and the third, and second and third are closer as compared to third and fourth. If you want to find the force on the wire or force on the charge placed in a magnetic field, so we will use Fleming's left hand rule. So according to Fleming's left hand rule, the first finger should point in the direction of magnetic field, the index finger. The second finger represent direction of the conventional current or the positive charge, and automatically the thumb will point towards the force or the deflection which the charge will experience, which is also known as a motor effect. So, example, you have two wires which are carrying the current perpendicular to the magnetic field, and we want to find the force experienced by each wire in a magnetic field. So what we can use, the formula is, if the wire is perpendicular 90 degree, so the formula is F is equals to BIL sine theta, but theta you can see the angle between the wire and the magnetic field is 90, and sine 90 is equals to 1. So that's why when wire is exactly perpendicular, F is equals to B, the strength of a magnetic field, I is a current which is passing through, and L is the length of a wire which is perpendicular to the magnetic field. Sine 90 is 1, so we will get this force. So wire will experience a maximum force when it is perpendicular. But if it is making certain angle, then we'll substitute the angle, or we'll take a component of the magnetic field which is perpendicular to the wire. So as you can see, this is a magnetic field and it is making certain angle with the length. So we always take a perpendicular component. You can resolve the magnetic field or you can resolve the length. So the one which is with an angle, that will be L cos theta here, and against the angle will be L sin theta. So L sin theta is perpendicular component to the magnetic field. That's why F is equals to BIL sin theta. But if there was a charge instead of a wire, if there was a charge moving in a magnetic field, if the charge enter exactly perpendicular, so it will follow a curve path. Like cross means magnetic field is into, and the only component for the motion was perpendicular to the magnetic field. So what happened, this charge will move in a circular path or curve path. But if it is making certain angle when it enters the magnetic field, or it is having two components of the velocity if when it is entering the magnetic field, so it was making certain angle. So if it was making certain angle, then because the velocity will have two components, horizontal and vertical. So it will be spiral, means it will move in a circular path, as well as it will move towards right or left according to the component. Because here when it entered, the only component of the velocity was there, and that's perpendicular. But in this case, there are two components of the velocity. One is perpendicular, one is parallel to, one is 90 degree. So, and another one is not affected because that's not 90 degree to the magnetic field, so it will follow a spiral path. So the path of charge vary depending on initially how many component of velocity it's having. Is it clear? And if you want to find the force on the charge in a magnetic field, so F is equals to B Q V. B is the strength of a magnetic field, Q is the magnitude of the charge, and V is the speed at which it entered the magnetic field. Is it clear? The force experienced by a charge or the wire which are placed in magnetic field. So the motor effect, basically what happens when we pass a current through a rectangular wire which is placed in a magnetic field. So there are two magnetic field. One is the magnetic field of a permanent magnet, which is from north to south. Another one is a magnetic field of a due to a current carrying conductor, which will be around the. So whenever two magnetic fields are there, it will interact with each other, and these two magnetic field interact and exert force. So which direction it will experience the force? We can use a Fleming's left hand rule. So Fleming's left hand rule. The first finger represent the magnetic field south. So first finger should point towards south. Second represent direction of the current, which is, if I label these sides A, B, C, and D. So current is passing from A to B. So for side AB, when we calculate the force will be down. For side CB or DA, because they are parallel or anti-parallel to magnetic field, not cutting the magnetic field, so it will not experience any force. But for side C and D, first finger represent magnetic field, second represent direction of the current, thumb is pointing up. So for CD, it is up. So it create a moment, turning effect, because one side there's a downward force, another side upward force. So what it causes? It causes a turning effect or the rotation. So the current can also cause a turning effect or produce a moment if the two forces are acting in opposite direction and acting away from the pivot. So this is a general mechanism, working mechanism for a DC motor. And what is electromagnetic induction? Electromagnetic induction states that the change in the magnetic field will induce EMF. Means if I change the magnetic field, I will produce EMF. So example, we have a magnet having north and south poles. So there are field lines pointing from north to south. So if you have a circular wire or a solenoid, a coiled wire, with the voltmeter, sensitive zero center voltmeter or galvanometer. So these field lines are passing through the solenoid as well. Now what happen if I move the magnet to and fro, like if I move the magnet towards or away, so this will produce a change in the magnetic field. And if there is a change in magnetic field, according to electromagnetic induction, what the the charges will experience a force, and without any power supply or battery, the current start to flow, or the needle of the voltmeter or galvanometer will deflect. That's called electromagnetic induction. And Faraday's law state that if we change the magnetic field at a faster rate, the EMF induced is directly proportional to rate of change of magnetic flux linkage. Means the EMF which induce is directly proportional to magnetic flux linkage. It gets denoted by N phi, because already we discussed the magnetic flux is B dot A. So magnetic flux is B dot A, and magnetic flux linkage is BAN. So in place of BA, I can write phi, the magnetic flux. So it will be phi n. And it is rate of change. So it means the magnetic flux linkage divided by time. So greater the change in the rate of change of magnetic flux linkage, greater the induced EMF. So how we can have a higher induced EMF? By moving the magnet faster, or moving the wire faster, or moving both of them towards each other, or away from each other. Both cases it produced change in magnetic field, but the one which was having a greater change in a magnetic field, higher induced EMF. So first we are moving a magnet with a speed of 3 meter per second towards a solenoid. So if this produce a voltmeter, because there's a change in magnetic field, voltmeter example record 2 volts. If we change the speed, like making 6 meter per second, so greater change in magnetic field, higher induced EMF. So this will be, because if speed is double, so this will be 4 volts. This is known as Faraday's law of electromagnetic induction, that induced EMF is proportional to rate of change of flux linkage. So generators uses the same concept. In case of generator, what we do, we rotate the wire, that produces a change in the magnetic field, and change in magnetic field induce EMF. And if you want to find the direction of induced EMF, we use Fleming's right hand rule. This is actually a motor is given, because this is having a supply, split rings are there. If it was a generator, then it will not have, this part will not have any source or a battery. This will have a load like resistor or anything. So when we rotate the wire, a generator can also be used, or uh, sorry, a motor can also generate electricity. If we rotate the coil in a magnetic field, there is a change in magnetic field, and that will induce EMF. And if we want to increase the induced EMF, we should increase the number of turns, use a large coil, use stronger magnet, or move at a higher rate. The Lenz's law of electromagnetic induction state EMF induced in such a way to oppose the change in the magnetic field. And the only difference between the Lenz's law and Faraday's law is a sign. The negative sign only we use to represent the different. What's the meaning? The EMF induced always oppose the change in the magnetic field. So example, you have a magnet which is having north and south pole. So you have a coil, a solenoid. If you are moving the magnet towards, there will be a change in the magnetic field. And due to this change in magnetic field, there will be induced EMF in the solenoid. But what happened? According to Lenz's law, EMF induced always try to oppose the change. So how it will oppose the change? The current will produce in the wire to oppose, because the change in magnetic field produce EMF and or current, and this current will produce in a direction so that it can oppose the change in the magnetic field. So if you are moving the magnet towards, the magnetic field is increasing, so this coil will try to produce a magnetic field which try to oppose this change. So how it can oppose this change? This side will be south, left hand side, and right hand side will be north. And if the direction of the current is in this manner, but if the same magnet, but we move in opposite direction. So if we move in opposite direction, this is also producing a change in the magnetic field. As there is a change in magnetic field, EMF will induce. But which direction induced EMF will occur? It will always try to oppose the change. How it will oppose the change? As a magnet is moving away, the strength of a magnetic field is decreasing. So this coil will try to increase. So how it will try to increase? This side appear, left hand side appear to be north, and the right hand side appear to be south. And the direction of induced current will be opposite to that of original. So if here the needle was deflected towards right, other case the needle will deflect towards left. So change in magnetic field induce EMF, but the direction of induced EMF is always try to oppose the change in magnetic field. Is it clear? So we can also use a graph of a coil or a magnet dropped through a copper tube. So example, if you drop a magnet down a copper tube, there's a copper tube and you drop a magnet. So what you will observe, it will drop slower than a non-magnetic material. Why it will drop slower than a non-magnetic material? Example, if we have a non-magnetic material, a material, say a a plastic tube is there, and you drop the same magnet with north and south pole, same poles, you will find it Through a plastic tube, it will fall faster, but through this copper tube, it is taking more time. What is the reason? Because what happened when the magnet is falling, there is a change in the magnetic field, so there will be induced EMF in the copper. Copper, because there is a current, so current is producing a magnetic field, and that current will try to resist the change in the magnetic field. That's why the magnet will slow down. So as a magnet falls through the tube, it will induce EMF in the copper tube, and this will cause a small current to flow around the tube, and the circling current will generate a magnetic field which will interact with a falling magnet, and the direction of the new field created is always try to resist the change. That's why it's try to repel or slow down. So magnet would end up with more kinetic. So in the beginning it will try, and what happened, like first when it is moving towards the center, because moving towards the center, the magnetic field is increasing, it will try to decrease, but moving away from the center, the magnetic field is decreasing, so it will try to increase. So in later case, when the magnet would end up with more kinetic energy, the gravitational potential energy, it has started, and this will be impossible. So law of conservation of energy dictates the Lenz law. And the EMF in the tube is such a way to slow a magnet. As a magnet is moved, it is creating an EMF. So you can see the next slide. This is a graph example. A magnet is passing through a coil. A copper coil is there. Now, there are two peaks. What is the reason for that? The reason is when it is moving towards and then moving away. So why the peaks? The two peaks are there. The direction of induced EMF will be different. As you can see, first it is moving towards the center. So and then it is moving away from the center. So induced EMF direction is opposite. And the second part, you can see one peak is higher than the other. What is the reason why one peak is higher than the other? The reason is because initially it is moving slower, later it will move faster. So faster movement means greater change. That's why one of the peak is higher than the other one. But the area of the two peaks, the first peak, it is broader, means greater area. So depth or height is small. The second one, small area, but the depth or the height is more. And what the area is representing, area under the both graph will represent n phi. What is n phi? Means magnetic flux linkage. Because the magnetic flux linkage or number of field lines passing through unit area through n number of turns is there constant. That's why area of both peaks is same. So what happened as the magnet enter the coil, there is a rate of change of magnetic flux linkage which induce EMF. As the magnet enter the coil, there is a force on it upward which try to oppose it according to Lenz law. As a magnet leaves the coil, the current direction reverses because the direction of the motion of magnet is opposite. The negative maximum of EMF is greater than positive. Reason for that, while leaving, so magnet has a greater speed when it is leaving as compared to as it enter. And the area of the graph will entering is equal to area while leaving, which represent the magnetic flux linkage and which is constant for. So magnetic flux linkage is the area under this graph. Is it clear? Then the last topic, it's transformer. Basically, a transformer consists of a soft iron core. The wire is turned around on this soft iron core. The coil where we connect a supply, that's called a primary coil. And where there is no supply, that's known as a secondary coil. We have AC input. Alternating input is there. So the characteristic of AC input, it is continuously changing its magnitude and direction. So current increase, then current decrease, then current increase, decrease, and reverses the direction. So change in the magnetic field. First, an AC input produces a variable magnetic field which magnetizes this iron. So this iron core will behave like a magnet. And the change in the magnetic field of iron core will induce EMF in the secondary coil. So without any connection between the two coils, this is called a mutual induction. When one material magnetizes the or produce a magnetic field, another wire by changing it. So AC input produce variable magnetic field, magnetizes iron core. So this iron core will behave like a magnet, and change in magnetic field of iron core will induce EMF in the secondary coil. Then a transformer, it only works efficiently with AC, does not work with DC because DC produces a magnetic field. A variable DC can be used, but constant DC cannot be used to produce induced EMF. And for a transformer, so we have a supply. The number of turn, how many times the primary is having turned, that's called NP. Voltage which we apply input VP, voltage which is produces VS, number of turns times the secondary turn, that's called NS. So the formula VS over VP is equals to NS over NP, or VP over VS equal NP over NS. If a transformer is 100% efficient, then the power input and the power output will be same. So input power is the product of voltage and current. So input is VP IP and output is VS IS. So if it is 100% efficient, power input will be equal to power output. And if number of turns of secondary are more than number of turns of primary, then we call that transformer a step up. But if number of turns of secondary are less than number of turns of primary, then we call that as step down transformer. So step up transformer used for power transmissions because they increase the voltage, reduce the current, so minimize the energy loss. And step down transformer like adapters, chargers use step down transformers which reduces the output voltage. And then the losses in the transformer, um, heat is produced because the current is having a heating effect. Heat is produced, so power can be lost in the form of heat. to mini or eddy current. Eddy current means because there's a change in magnetic field of the core. So due to this change in the magnetic field of a core, the current also produced in the core, but that's a random movement, like not in a specific direction. Randomly, the charges start to flow. So that reduce the strength of a magnetic field. So iron will not be 100% magnetized, loss in magnetization. So how we can minimize these losses? So to reduce this loss, we use a laminated iron core. So basically we use thin sheets of iron instead of using a one piece iron. Like thin sheets are there, and we wrap the wire around these thin sheets instead of using one piece. So what's the advantage? It will have a large surface area, so it will cool down faster, minimize the eddy current as well. So this was about magnetism. So we are done with unit 4 of A2 physics. Next time we will discuss the past paper related to unit 4. Any question related to the class today? Any question or doubt? Okay, so I'll end the session and share the recording. In next class, we'll do unit 4.